Welcome to part 4 of our How to Design and Build an Airplane series. In this video, we're going to be doing the aerodynamic design of the tail. I've primarily used Aircraft Design, a Conceptual approach by Raymer as my guide for this project. The information can be found below. Just like with all the calculations I did for the main wing, all of these calculations were put into an Excel spreadsheet to make design iterations easier. In case you've forgotten, we're going to use a conventional tail on this airplane. This tail is comprised of two main pieces, the vertical and horizontal stabilizers. Now these two pieces are going to be based off of a percentage of our main wing area. If you opted to go with a different tail configuration, you may still be able to use some of these if you're comprised of vertical and horizontal components. If you're using a V-tail, for example, you're going to have to look somewhere else for how to size those. For our horizontal stabilizer, we're going to want that to have about 20 to 22% of our main wing area. Meanwhile, our vertical stabilizer is going to have 6 to 8% of our main wing area. This makes the surface area of our horizontal stabilizer 40.4 square inches, and our vertical stabilizer will be 14.12 square inches. Just like with our main wing, we need to select an aspect ratio for our tail. The tail aspect ratio for a subsonic airplane usually falls between 3 and 5. If you stay on the lower end, you're going to have a lighter structure, and if you go towards the higher end, you're going to have less drag. We're going to try and keep our tail light, so we're going to go with an aspect ratio of 3. If you remember, aspect ratio and surface area are both found using span and chord. Aspect ratio is equal to span divided by chord, and our surface area is span times chord. So we have here two equations and two unknowns, so we can solve for both span and chord. So first we're going to solve surface area for span, and we end up with surface area divided by chord is equal to span. And then we're going to substitute that into our aspect ratio equation. So we end up with S over chord divided by chord is equal to the aspect ratio. And you rearrange that to get chord by itself, and you end up with the square root of the surface area divided by the aspect ratio is equal to the chord. So we found out that our chord is going to be 3 9/16, and then going backwards we calculate our span to be 11.315 inches, or about 11 5/16. This isn't the method that I used originally, but I found that it worked better, so this is the one I'm explaining to you. We ended up with a final aspect ratio of 3.15. The last thing we need to do here is determine the height of our vertical stabilizer, and using the same chord that we had for our horizontal stabilizer and the area that we calculated earlier, we find that our vertical stabilizer needs to be 4 inches tall. Now that we have the dimensions set for our tail, let's calculate the lift and drag that it's going to be creating. In general, the tail is used to counteract the pitching moment from the main wing, along with helping to control the aircraft. So, knowing this, we're going to move backwards from using our pitching moment to calculate a force required for our tail, and then into calculating the lift coefficient we need to generate that force. So we know our main wing has a pitching moment of minus 0.35 foot-pounds, and we know that our tail is going to be 11.5 inches back. I'm going to explain how I got to this number later, don't worry. In order to get a force, we have to multiply our torque times our distance. So it's going to be minus 0.35 foot-pounds times 11.5 inches, once again divided by 12 so you can get it converted into feet. This gives us a force of minus 0.33 pounds. So now we move back to our lift equation, which is lift is equal to coefficient of lift times 1/2 rho v squared surface area of our wing. And we're going to solve this for coefficient of lift. And we find that coefficient of lift is equal to lift divided by 1/2 rho v squared surface area of the wing. So we're going to plug in our numbers. Our lift is equal to minus 0.33 pounds. Our density is equal to 0.00238 slugs per cubic foot. Our velocity is 55 feet per second squared, don't forget that. And our surface area is 40.59 inches squared, and we have to divide that by 144 as usual to make sure it's in feet squared. And then we find that our coefficient of lift is equal to minus 0.0023. Now, if that sounds like a really small number, that's because it is. In order to get such a small coefficient of lift, we need to use a symmetrical airfoil. The reason we're going to use one of these is that when they have 0 incidence, they have 0 coefficient of lift. So the question on your mind is probably, why are we even using an airfoil if we're not trying to get any lift from it? Hypothetically speaking, you could use a flat plate. The problem with using a flat plate, though, is at 0 angle of incidence, it works just fine. The air flows over the top and bottom smoothly, and everyone's happy. But when you add some incidence to this, you have the air flowing nicely along the bottom where there's going to be high pressure. But then on the top, you have what's called boundary layer separation, and you end up with the air slowing down a lot, And thanks to the Bernoulli principle, when the air slows down, it also gains higher pressure, so you lose a great amount of control. So when you have a symmetrical airfoil, you don't have this boundary layer separation, and you're allowed to direct the air more efficiently. So when we have zero angle of incidence, we have zero change in direction of our air and zero force in either direction. But when we add incidence to the airfoil, the air sticks and can be directed downward or upward, generating either lift or downforce. Now, we're not going to be moving the entire horizontal stabilizer. We're just going to have an elevator at the back end of it. These advantages still apply when we use just an elevator at the back of our airfoil. So knowing this and also trying to limit our drag, I selected the NACA 0008 airfoil. So now we're back on airfoil tools, and we need to find what angle of incidence for this airfoil will give us our 0.0023 lift coefficient. So when we look at the table, we find that the first point at minus 0.25 degrees gives us a lift coefficient of 0.0087, which is about 3 times higher than we need. And not to mention, I can't build anything in balsa wood that accurately. So looking at this chart, we're going to go with 0 degrees angle of attack, and we're going to pull out our coefficient of drag. Now that we know we're not going to try to generate any lift with our tail, we're just going to adjust with trim to get the force we need. We need to calculate how much drag the tail is going to generate. So we go back to our drag equation, and this time it gets a little bit easier. We no longer have induced drag because we're not generating any lift, and if you remember correctly, the induced drag was based on the coefficient of lift. And if our coefficient of lift is 0, our coefficient of induced drag is also 0. Now we're going to plug in our numbers. Our coefficient of drag from airfoil tools is 0.0052. We have our 1/2 rho v squared, which is 0.00238 times 55 squared. And then for S wet for our tail, we need to include both our horizontal and vertical stabilizers. So that's going to be 54 inches squared divided by 144, so we get it back to square feet. And we find that our drag force for our tail is 0.00528 pounds. The next thing on the to-do list is to explain where I got that 11.5 inches for the tail length in the beginning of the video. You can place the tail anywhere you want, but it's going to be easiest if you put it behind the main wing, like just about every airplane you've ever seen. There's 2 main things that we need to avoid when picking a spot to put our tail. This first spot in green shows an area that, if we were to get into a stall, would be very turbulent. Having turbulent air pass over your tail is going to cause it to not have any control, and it'll be very difficult to recover from a stall. This figure from Raymer's book shows the area to avoid. The next thing we need to avoid is the downdraft from the main wing. Now, if you remember, one of the things that I said created lift was redirecting the air from a horizontal path to a more downward direction. We need to avoid this downdraft area because that's going to change the effective angle of attack of our tail. Now, this area can be found by drawing a tangent line from the top surface of your wing going down. What is a tangent line? Well, I'm glad you asked. If you draw a circle and then you have a straight line that only touches one point of that circle, that's a tangent line for that point of the circle. Using this area we laid out with the tangent line in that diagram I showed you from Raymer's book, we opted to put our tail 2 1/4 main wing chords behind the quarter chord position of our main wing, which works out to be 11.5 inches. Now we're just going to go back real quick and do something that I should have put in the beginning of this video, but didn't. I just want to talk about the sizing of our control surfaces. Now, just like our tail, they're going to be a percentage of our main wing or vertical and horizontal stabilizer areas. For our ailerons on our main wing, they're going to be 6% of our main wing area, making them 11 square inches. Our elevator is going to be 20% of our horizontal stabilizer area, making that 8 square inches. And our rudder is going to be 33 to 50% of our vertical stabilizer, making that 4.7 square inches. When you're choosing the dimensions for your control surfaces, you want to try and make them something that you can actually build. You don't want a really long aileron that's only 1/8 inch wide, because that's going to be really difficult to build and support on your aircraft. Instead, you might want to go with something that's way shorter, but about 1/2 inch wide. That's it for part 4 of our How to Design and Build an Airplane series. In this video, we designed our tail, figured out where it was going to be placed, and sized our control surfaces. If you have any comments, questions, concerns, ideas for other projects, please leave them in the comments below. Follow us on Twitter and Instagram @HugeBears. Thanks for watching. Please like, share, and subscribe.